this video, I'm going to do some examples on solving first order ordinary differential equations using Laplace transforms. So this is part of a series of videos where we go through Laplace transforms, including the basics. So this is the definition of the derivative of the Laplace transform of the derivative. So we have e to the power of negative st, and we have the derivative function here. If we integrate by parts, we have the e to the negative st and the integral of the derivative, which gives us the function. Then we have the derivative of this, and then we have the integral of the derivative, which gives us the function as well. When we work everything out, we have this function here, and you can see on this side that this is the definition of the Laplace transform of a function, because we have e to the negative st. So we know that the derivative of a function of t, and if we Laplace transform the derivative of that function, then we have negative function with 0 in, plus s multiplied by the Laplace transform of the function. So if we do an example to show how this can be incorporated, we have an example here. We have the derivative function plus 2 multiplied by the function equals 12 minus 4e to the power of 2t, where the function at 0 is 5. So first what we're going to do is we're going to Laplace transform the whole this whole equation here. So the proof above has just shown that the derivative of the Laplace transform of the derivative is this. So we'll write this down, minus f plus 2 multiplied by the function. So the Laplace transform is plus 2 equals 12 is just 12. And then if we look on the tables, so on these tables here, we're going to find the Laplace transform of 4e to the 2t. So 4e to the 2t here, e to the 2t, so it will be 4 over s minus 2. So we have minus 4 over s minus 2. So now that we've got that, we're going to manipulate the left-hand side to just get the Laplace transform of the function. So we know that the function at 0 is 5. So we have negative 5 plus, we're going to factorise the Laplace transform of the function multiplied by s plus 2. And then on the right hand side, we're going to combine this function. So if there was a 1 under, so we would have 12 over 1 minus 4 over s minus 2. But if we have a 5 here, we can move this across. So if we have 5 plus 12 is 17. 17 over 1 minus 4 over s minus 2. Now we can combine. So we have, if we just do it here, the Laplace s plus 2 equals, so we have s minus 2 on the bottom. We have 17 multiplied by s. 17 multiplied by minus 2. And then 1 multiplied by minus 4. So if we write this down here, we can divide both sides by s minus 2 as well. So we have the Laplace of the function equals 17s minus 38, all divided by s plus 2 multiplied by s minus 2. So once we've done that, we're going to use partial fractions to separate them. So the function is going to look like a over s plus 2 plus b over s minus 2. So to use partial fractions, I've got a separate video on how to do that, so I'm just going to explain through here. So we do a multiplied by s minus 2 plus b multiplied by s plus 2 equals 17s minus 38. Once we've done that, we can substitute in values for s to make two simultaneous equations or identify a and b. So if we substitute in 2, s equals 2, this term comes to 0 because 2 minus 2 is 0, anything times 0 is 0. So we would have 2 plus 2 is 4, so 4b equals 17 times 2 is 34. 34 minus 38 is minus 4. So b equals minus 1. If we do s equals minus 2, then this term would equal 0, and then we would have minus 4a equals 17 times minus 2 minus 38 is minus 72, and then we divide by 4, and that gives us 18. So we have our Laplace transform equals 18 over s plus 2, it's minus 1 over s minus 2. So if we continue on the next page, so I'll just write again the partial fractions we got. So it was 18 over s plus 2 minus 1 over s minus 2. So now that we've done that, we can use the table of Laplace transforms to find the inverse. So if we look at our table, so we have s plus 2. So looking at the table, I'm thinking it's this one because it's got a single s. So the function will be 18e to the negative 2t minus e to the 2t, because we have to pay attention to the positive a here and the negative a here. So that's how you would use Laplace transforms to solve first order ordinary differential equations.